So today we're going to be looking at a barrel or a tank that is free to roll around, and we're going to be looking at the pressure or the force exerted both on one of the end caps as well as one of the sides of the tank. So the reason that we're looking at this in terms of a freestanding barrel or a barrel that is free to move around if a force is exerted on it is because we know that the pressure on each side of the tank or the force exerted on each side of the tank is zero if the barrel's not moving. So in this case, we're going to start off by, and this is just for visualization, if we have some fluid up to fluid level H, and it goes down to depth 0, or a better way to write this would be have this be 0 and depth H. And then the best way to go about this is to pick a cross-sectional area to use to help us with our integration. And we want that to be equal for both sides and also as large as it can be. So since our tank is symmetrical down the center axis, we can choose a rectangle going right down the middle up to the fluid level H. So the way that we can express the total force exerted on the side is we know that force equals pressure over area. So force is just going to be equal to the integral of pressure times dA. In this case, or sorry, what am I thinking? Pressure equals force divided by area. In this case, the way we can go about this is re-expressing our area of our strip here in terms of smaller strips with height h as well, and we'll mark it so we know, and then multiply that by the length. So the area of this strip is just going to be L times H. So a way we can re-express our dA is simply L times H times dH. And then we can also substitute for pressure. So our pressure is going to be rho g times L. Sorry, this is the pressure. But our full expression is going to be rho g times L times H. And this H doesn't represent anything in the real world. It's just a way to aid us in visualizing and mathematically helping us with the integration. So we're going to mark it as a dummy variable of integration times dH. And from here, the integration is very simple. Force is going to be equal to rho g, L are all constant, so we can just rewrite those. Oh, sorry, I forgot. In this case, to find the total pressure based on the height of the fluid, we need to integrate from our 0 point to our full depth. So we're going to go from 0 to H. Okay, so back to the integral. Rho g and L are all constants, and then that'll just leave us with H squared over 2 integrated from 0 to H, which is also going to be rho g L H squared over 2. So that's our equation for the side of the barrel. But if we want to look at one of the end caps, it's going to be a little more complicated. So now we're going to be looking at one of the circular end caps. In this case, we're going to use a similar formula to before, or a similar integral, rho g H times dA, and that's going to be our total force. We have fluid level H, same as before. It doesn't matter if the fluid level is above or below the midpoint. And we have these two sections of this entire circular segment here. And we're going to just be looking at this half right now because we can just multiply by 2 later on. So here we're going to have theta 1 and theta 2. Theta 2 is just going to be equal to pi over 2. We don't need to worry about that right now. And our goal is to figure out how to express our theta 1 here. So theta 1 is going to be equal to this segment here times our hypotenuse, or the arc sine of this segment here over our hypotenuse, which is just our radius. And this segment here, it's going to be equal to our fluid level minus our radius. So we know that theta is going to be equal to the arc sine of h minus r over r. So to find the area, the total area of our fluid here, well, the portion of the area covered by the fluid, we can draw these little strips in. And similar to before, we're just going to find the area of each of these strips and plug that in. So our final goal is to find an expression for dA. Well, the way to go about that first is to find an expression for the height of our strip. And in this case, each of these strips is just going to be r cosine theta. That's the length of the strip. So our dH is just going to be r cosine theta d theta. It's relatively simple. So in that case, our dA, our A, is going to be equal to our r cosine theta, and once again that's our length, times r cosine theta over d theta. Sorry, I got tripped up there. This is just going to be dH over, or r cosine theta d theta over dH. So we can rewrite dA as being equal to r squared cosine squared theta over dH, and then d theta. So going back to our equation here, or our integral here, the integral of rho gh times our height times our dA is going to be equal to our total force. Actually, quick correction, it's going to be 2 times our integral here, because once again we're only solving for 1/2 of the face. So we can go ahead and start plugging in. You can probably hear Carter. If we start here, we can pull out rho g. So we'll have 2 rho g, and then the integral of h. And real quick, we can re-express h as r plus r sine theta. And again, if you look at this, this little triangle here, it's pretty simple. We have our r, that brings us up to the midpoint, and then the area above the midpoint or below the midpoint, depending on the angle, is just going to be sine of the angle times our radius. So we can rewrite our h as r plus r sine theta, and then we can plug in our expression for our dA, r squared cosine squared theta d theta. Now that we have our integral, we just have to define our limits of integration, and then we can just plug it into an integral solver like Wolfram Alpha. Once I can get it, just my camera. Okay, so our limit of integration, and sorry, I misspoke earlier, that should be negative pi over 2. Our limit of integration is simply going to be from negative pi over 2 all the way up to theta. So 2 rho g integral from negative pi over 2 to theta. Carter's chilling in a fabric box of r plus r sine theta r squared cosine squared theta d theta. I kind of ran into our barrel there. So we're going to go ahead and plug that into an integral solver. Let me pull up Wolfram Alpha here. All right, so actually let me window this real quick. So if we are going from 2 rho G, we'll leave that out of there for now because we can just rewrite that ourselves. The hardest part about this is figuring out how to get the online calculator or Wolfram Alpha to do what we want it to do because it doesn't have the capability, at least not the free version. I'm not willing to pay for the paid version. It doesn't have the capability of substituting in. So we just need to re-express our theta in terms of our arcsine of h minus r over r. So we'll go ahead and do that. Sorry, I'm trying to type up here and then look at what's going on down here. So we're going to integrate from, well, we're not going to type that in yet, but we have r plus r sine theta, and I'm just going to use I could type in theta, but it takes longer. And then r squared cosine squared theta. Let me make sure that's in parentheses. All right, and then we need a matching parenthesis. And then we're integrating with respect to theta. All right, so that's our outer parenthesis. And we want to evaluate from negative pi over 2 to theta. And in this case, we need to re-express that as negative pi divided by 2 to arcsine of h minus r divided by r. And then I need another set of parentheses. Sorry, I'm looking at my feed of my screen down here now in OBS. So that looks good. And then we just need an equal sign, or from theta equals negative pi over 2 up to arcsine h minus r over r. And why don't we go ahead and we'll just include the 2 rho G. And go ahead and evaluate. Looks like we missed some set of parentheses here. That's usually what happens when trying to figure out what went wrong. All right, give it another shot with without the 2 rho G. There we go. Takes it a second. All right, so our, I see. It actually ran out of time to do, no, here we go. So this is our final solution. We just have to plug back in our 2 rho G. So finally, all we have to do is use the 2 rho G. So force is going to be equal to 2 rho G. We have 1/12 r cubed. I don't know why it's, see that? This pen must have kind of messed up. And then obviously this 2 and 1/12 we can just combine to 1/6. And then we have 2h minus 3r times the square root of negative h times h minus r. Looks like a k there. Over r squared times h plus r all over r squared plus 6 arcsine of theta h minus r over r plus 3 pi. So that is our formula for the force being applied to the end cap of, well, one of the end caps of our cylinder.